Okay. Never mind. Okay. Good evening. So I just looked at the calendar. So we got 2 more weeks before the final lecture, which will be scheduled for the examination. Okay. So I need to. So obviously I won't be able to finish all as originally planned. So I will focus on some of the important items to go through in this coming 2 weeks. Okay. And then I will spare some time to talk about the scope of the examination. Okay. So I see some of you are laughing because that obviously seems to suggest those things that I'm trying to cover will be very important, right? But again, don't take don't, how should I put this? So the stuff I am going to cover, I won't guarantee it will appear in the examination, okay? But it's just something I feel is important to know as a course. So don't blame me if you don't see those things that I cover appears in the examination at the end, all right? So, but still they're important. Okay, so let's talk about the power control. So last time we talked about the call processing. So what happens after you press the send button? So now let's move on. Because IS95 is a CDMA system. So as we talked about last time, in the uplink of the IS95 is operating based on random CDMA. And then the capacity, how many users you can support in random CDMA, depends on how much interference you can tolerate, right? Because every time you invite a new user, the new user will contribute a little bit of delta, right? So in order for the random CDMA to function properly, when we analyze the capacity, we made a very important assumption that the power received by the base station from the mobile, no matter where is the mobile, whether it's close or far away from the base station, the received power is the same, okay? And so that everybody contribute equally. Everybody contribute an equal delta to the interference level. And that will be the optimal situation. But then how do you achieve this condition? So this is done through power control, okay? So now let's talk about the power control algorithm. Now the power control is not, so let me just draw the picture. So once again, if this is the base station, we see power. And then this is time. So in general, as the mobile, suppose there is no power control. As the mobile move around in the coverage area, so the receive power picked up by the base station, of course, will not be a constant, right? It will fluctuate up and down like this. And then as we talked about many lectures ago, these variations, there are 3 factors that contribute to these fluctuations, right? The first is path loss. As the mobile move, the distance separation between the base station and the mobile changes, right? And that induces a change of the receive power, right? And we'll also talk about this is the dynamic range. It's around 140 dB. Okay, so depends on the cell size. For a typical medium-sized cell, let's say 1 kilometer cell radius. So the dynamic range between the strong signal and the weak signal can be 140 dB or above. Now, the second factor that would affect, that contribute to this variation is the shadowing. Shadowing, the dynamic range is like 8 to 10 dB. And then the third factor that contributes to this is the fading, right? And the fading, the dynamic range is around 30 to 40 dB. Okay? So all this added together, you can say that you can see the worst case dynamic range typically would be 200 dB, okay, or above. So now, as I said, right, if this is the random CDMA uplink, right, reverse link, if there is no power control, that means that we see power fluctuations from a single user can be up and down by 200 dB. With this 200 dB, and that means the best case and the worst case user can be differ by 200 dB, and that's a lot, okay? So therefore, the goal of the power control is to suppress this fluctuation. The ideal case is, in the ideal case, we want the receive power from everybody is the same, given by some parameter S, okay? That's the ideal case. But in practice, we won't be able to achieve this perfectly. So there may be some residual fluctuations. So these fluctuations, I call this delta. this fluctuation will be translated to capacity loss in random CDMA. Okay? So the larger this fluctuation is, the more capacity will be lost in a random CDMA. So therefore, the goal of power control design is to suppress this fluctuation as small as possible. So that's the objective of power control. Okay? So now let's look at how in CDMA, in IS95, how this is done. So in IS95, because we're talking about reverse link, so the power control is called reverse link power control. Reverse link power control means it is controlling the transmission power of mobiles. It's not controlling the transmission power of the base station, because that would be downlink. Now this is for uplink. So it's controlling the transmission power of so it's control UE transmit power. Okay, so that's called reverse link power control. So how do you do it? The goal is to make sure that the receive power at the base station side. So base station as a receiver, you will receive the power from every user with very small fluctuations, as small as possible. Okay? So it's quite complicated. So the first component is called open loop power control. Open loop power control. Open loop, that means there is no feedback. The receiver and the base station, you guys are the mobile transmitter. You guys are talking to me. With open loop power control, that means, remember, so in this analogy, you imagine you guys are mobile, but you're blindfolded. You don't see me, so you don't know where you are in my coverage area. Okay? So when you talk to me, with open loop power control, you have to figure out what kind of power you should use to talk to me. Okay? So I won't tell you what kind of power you should use. So that's called closed loop. The other component is called closed loop power control. With closed loop, that means I will give you feedback. I will give you very frequent feedback. So it's 800 hertz closed loop power control. That means over 1 second, I will give you 800 independent power control command. I will tell you whether you should increase your voice or decrease your voice during the communications, during the traffic channel conversation. Okay. And by the way, let me erase this. What do I want to say? 800 hertz. I forgot. Anyway, so okay, so here I will tell you, okay, yes, remember. So this reverse link power control will kick in only when you have a traffic channel. That means only when the traffic channel in both uplink and downlink is allocated to you. Then you start to have this reverse link power control. Okay? In other words, if you're in idle state, when you're in idle state, as we talked about last time, there is no dedicated traffic channel allocated to you. So you don't have to pay for anything. So during this idle state, there won't be any closed loop power control controlling your power. Okay? Okay, so now these are the, so furthermore, the closed loop is further divided into something called inner loop power control and outer loop power control. Is that okay? So it's two components like this. Okay, so now let's explain this. Now it looks complicated, but in fact it's very intuitive. First of all, open loop power control. So how do you know what kind of transmission power you should use when you talk to me when I'm not giving you any feedback? Remember, the overall dynamic range, the fluctuations of the receive power is due to path loss, shadowing, and fading, right? So let's say path loss. Now I'm talking, as you see, right, the base station always have downlink transmission. There is always a pilot channel, sync channel, paging channel transmission, right? So that means I'm always talking. Now you blindfold yourself. Of course, you don't know where you are. But if you listen to my voice and you hear me, my receive, if you hear my transmission and the receive power is very small, okay? Then what does that mean? That means you're close to me or far away from me. If you hear my voice my voice is very weak to you. That means you're far away from me, right? Okay? So if you're far away from me, that means the path loss, downlink path loss will be large, right? So if the downlink path loss is large, then what about the uplink path loss? Will it be large or small? Of course large, right? Because path loss is symmetrical, right? Path loss is due to distance separation. If from the base station to mobile, path loss is large, then the reverse would be the same, right? Okay? So therefore, the opener power control is just doing something like this. Mobile transmit power should be inversely proportional to the RSSI, receive signal strength indicator. This receive signal strength indicator is the signal bar that your handset displays. So when you're in idle state, you listen to the broadcast from the base station, and that will give you some signal strength indication, right? Sometimes if we receive strong signal, you have this full bar. Sometimes when you receive weak signal, you only have half bar, right? Your handset will have this indicator. So this indicator is the receive signal strength indicator. The receive power, the overall receive power from the base station to you, okay? So you want to make your mobile transmission power inversely proportional to this, because if you receive a weak signal, if you receive a small RSSI, that means you are likely to be far away from the base station. If you are far away from the base station, your transmission power should be increased, right? So that means if you are on the corner of the classroom, when you talk to me, you should be shouting, right? Whereas if you are close to me, your RSSI from me will be very large. And then when you talk to me, you should use your soft voice, right? Okay? So it's very simple, common sense. Now with this simple arrangement, as I said, you can neutralize the path loss, right? Because if the downlink path loss is large, the uplink path loss will automatically be large. So with this arrangement, you neutralize the fluctuation due to the path loss component, right? Which is 140 dB. So you take away 140 dB fluctuation from this, which is nice, right? Remember, our goal is to suppress these residual fluctuations. If you do not do anything about this, the fluctuations will be 200 dB. Now, by doing something like this, you take away the dynamic range contributed by the path loss, which is 140 dB, right? So the remaining fluctuations could be due to fading and shadowing, right? So this is nice. It helps to reduce, just simple rules like this help to reduce the dynamic range of fluctuations. Now, what about shadowing? Can you neutralize the shadowing with this arrangement? Now, shadowing is talking about blockage, right? If the downlink signal is blocked by a tree, what about the uplink signal? It's also blocked by the tree, right? So blockage is also symmetrical. That means if I can see you, you can see me as well, right? Okay? So by doing this, you can also neutralize the shadowing effect, which is 8 to 10 dB. So with this, you take away 140 dB from path loss, you take away 8 to 10 dB from shadowing. Okay? Now, what about fading? Is the fading symmetrical? If the downlink fading is large, what about the uplink fading? Would that be large or small? Now, that is something you need to be careful. Now, for IS95, it's based on something called FDD, frequency division duplexing. That means the uplink transmission and downlink transmission happens simultaneously, but on two different frequency bands. So in the frequency spectrum, this is usually the uplink spectrum, and then this is usually the downlink spectrum. So when operator get a license for FDD systems, this is called pair spectrum. The license have to come in pair, one for uplink, one for downlink, okay? And that's why this is more constrained. So pair spectrum usually is more expensive because it's hard to find, so it's more expensive. So for this IS95 system, the spectrum always arranged in pair system. So now if you have a downlink fading, the downlink fading is operating at this frequency. Uplink is operating at this frequency. The separation is called duplexing frequency. Usually it's something like 75 megahertz. Okay? It's also defined in the standard. So now if from the downlink transmission, you see alpha downlink is large. With this, what can you infer from alpha uplink? Alpha uplink is large or small? What can you say? There is no correlation because alpha downlink and alpha uplink, in this case, if you look at the correlation depends on the frequency separation, right? In this case, the frequency separation of 75 megahertz would be much larger than the coherence bandwidth. Coherence bandwidth for indoor is 1 megahertz, for outdoor is 100 kilohertz. So with this kind of frequency separation, the two fading coefficients in downlink and uplink are uncorrelated. What do we mean by uncorrelated? That means if the downlink fading is large, it doesn't change the chance for uplink fading to be large or small. So in other words, they are independent. If they are independent, so by doing something like this, you can neutralize the path loss, you can neutralize the shadowing, but you cannot neutralize the fading because the downlink fading and uplink fading are not symmetrical. Is that okay? So therefore, with this simple open loop, you cannot do a perfect job, right? And of course, if you can do a perfect job, you don't need closed loop anymore. So with this open loop power control, the only thing is the residual fluctuation will be due to fading, which is around 30 to 40 dB. So what you did, the contribution of open loop is not to do a perfect job in power control, but it helps to suppress the fluctuations from the initial 200 dB to something like 30 to 40 dB. Is that okay? So therefore, the closed loop power control will have an easier job. Now, without open loop power control, if you put all the burden to the closed loop power control has to handle an initial fluctuations of around 200 dB, which is much more challenging, as you will see later. Okay? But with the presence of open loop power control, you will still have some residual fluctuation, but it's around 30 to 40 dB fluctuation. So the closed loop power control will have an easier job to do. Okay? Now, so that's open loop power control. So here is an illustration. So if this is, let's see, this is what we see. This is our SSI. Okay? The signal strength received from the mobile station from the base station. Okay? Received at the mobile station from the base station. So mobile receive power. Okay? Our SSI. So you see that our SSI is decreasing. So that means this particular mobile is actually moving away from the base station. Right? It's leaving the base station. So in response to that, that is the mobile transmit power. The mobile transmit power is increasing because it's inversely proportional. Okay? So that's the reverse link power, that's the open loop power control. So this is open loop because nobody is giving you commands, asking you to increase or decrease your power. So you do it automatically by yourself. Okay? Now, with this open loop power control, let's focus on the first component, in loop power control, closed loop power control. So let me erase this. So let's try to introduce the, so this is a base station receiver. So there is a inner loop power control. Let's try to introduce this using a black box approach. So there is two inputs. One is the SIR target for the uplink traffic channel. Okay, this is for traffic channel. So at the base station side, there is a target receive signal to interference ratio, or target receive power, to make it simple. Okay, and then this is an actual SIR, also on the uplink traffic channel. So this is the actual measurement. This is a target, and then the output. The output will be a 1-bit power control command. Okay, so this 1-bit power control command can only signal two actions, either increase or decrease by a certain power, delta. So when this guy issue a positive power control command to the mobile should increase the power by delta. If this guy issued the inner loop output power control, issue a negative power control command, the mobile station should decrease the transmission power. Okay? And this power control command, which is 1-bit, will be repeated. I mean, this inner loop power control block will send 800 independent power control commands every second. So this is 800 Hertz. So it's very fast. Over 1 second, there are 800 independent commands. So in the analogy, I'm the base station. So my inner loop power control would be, I would generate 800 independent commands. So every time I will tell you to either increase your transmission power or decrease your transmission power. Okay. So obviously the operation is very simple. So I would ask the mobile to increase your power. Okay. So if you're talking to me, so pretty much the idea is I try to hear your transmission, right? If your voice is too weak, then I will ask you to increase your power, right? Increase your voice by delta. If your voice is too loud, then I will ask you to decrease your transmission power. So it happens 800 times every second. So I will generate a positive power control command if the SIR actual is less than the target. Right? If this is less than target, that means your voice is not strong enough. Then I will ask you to increase your voice by delta. Otherwise, I will ask you to decrease your voice by delta. So this is how internal power control generate the power control commands. So very straightforward, right? So let's look at a toy example. Now in this, this is y-axis is a base station receive power, okay, or base station receive SIR in dB. So this is the actual, the solid line is the actual SIR for the uplink traffic channel, measured by the base station as well. Now let's say this is the target. Okay, this dotted line is the target. So obviously the initial actual SIR is above the target, right? Now this is above the target. So according to this rule, the base station will send a power control command of negative. So in response to this negative power control, the mobile transmission power will be reduced by delta. So this is delta. Okay? So therefore your receive power base station receive power will then be decreased by delta. And then you go to compare the measurement. The actual SIR is still above target, right? So you keep on sending a negative power control command. Mobile transmission power is further decreased by delta. So you keep on decreasing like this, okay? Now until when? Until when you are close to this target level. When you are close to this target level, we call this steady state. In the steady state, what happened? Now your actual receive power will not stay at the target because I only have one bit power control. I can only allow two actions, either increase or decrease. I cannot ask you to stay unchanged, right? So therefore, in the steady state, what happens is the receive power will oscillate up and down between plus delta and minus delta, so that on average, you reach the target level. Okay, so this is called the steady state. On the other hand, this is called the transient. So you have a transient and a steady state. Is that okay? Now, in this example, this transient is undesirable. Why? Why this transient is undesirable? So in fact, you want to, if you have a choice, you want to get out of this transient as soon as possible because this is undesirable. Why this is undesirable? In this region, what happened? In this region, what's wrong with that? Staying in this region for too long. This region means the mobile is transmitting more than what it is needed, right? What is needed is this level. But mobile transmit power is excessive, right? So what's wrong with transmitting excessive power by the mobile station? If this particular mobile is transmitting excessive power, that means, don't forget this is operating in random CDMA, right? So that means this particular user will contribute extra delta as interference to the others. If this guy contributes more than sufficient delta, then that means there's less room to allow for other users. Is that okay? Because the number of users you can accommodate depends on how much extra interference you can tolerate, right? If this particular guy transmitting excessive power, then that means the extra headroom for allowing other users will be reduced, and that will reduce the potential capacity of random CDMA. Is that okay? So this is undesirable. If your system, if your base station design always have this transient here, then your capacity will be lower than your competitors. Is that okay? So this transient is undesirable. Now, what about if you start with a below target and then you gradually warm up to this steady state? That is another type of transient, right? If you start below the target and you stay for a long time in this other transient, what's wrong with that? That is also undesirable, right? What's wrong with that? If you start below target, that means you are not transmitting sufficient power, right? If you are not transmitting sufficient power, that means the uplink traffic channel will have high error probability. If your uplink traffic channel has high error probability, if this persists for too long, the base station will declare link failure and it will drop your call. Is that okay? So if you stay in the other side transient for too long, your uplink traffic channel may be failed, may be regarded as failure, and then the call may be dropped. So then in this case, you will trigger a lot of call drop probability. If your base station have the other types of transient for very long, that means the call drop rate for your base station would be higher than your competitors. Is that okay? So therefore, transient is undesirable. We want to get rid of transient as soon as possible. If you stay for the transient, either the up transient or down transient for too long, then you will either end up having less capacity or extra high call drop rate. Okay? So you want to get out of transient. Now the only parameter we have in this inner loop power control is this delta. Okay? This delta is something you can control. Now for the sake of getting rid of transient, getting away from transient, moving out of transient as soon as possible, would you prefer large delta or small delta? Would you like to use a large delta or small delta? If you want to get out of this transient as soon as possible. Of course you want large delta, right? Because think about if you use a small delta. If your initial offset is 30 dB, then it takes you many, many power control steps before you can reach the transient, right? So, but if you use a very large delta, 10 dB every time, then it takes you 3 power control commands to reach the steady state, right? So from the transient perspective, you prefer large delta. Is that okay? No, but however, what's wrong with large delta? If you use large delta, then when you're in steady state, what will be the fluctuations? The fluctuations will be up and down about delta, right? So that means with large delta, the steady state error will also be large, right? Remember, what is the goal of power control in the beginning? We want to suppress the fluctuations as low as possible because the larger the fluctuation you have, the larger the capacity loss would be resulted, right? So you are concerned about in the steady state, you want to keep the fluctuation low, right? So therefore, from the steady state error perspective, you prefer small delta. Is that okay? So therefore, the design of delta is a trade-off. Now, why do I say the open loop power control will make the life of closed loop easier? Now imagine you don't have open loop power control. Then that means the initial offset could be 200 dB. You can be 200 dB away from the target. Now if this is 200 dB away from the target, do you have the luxury to use a small delta? If you use a small delta, then it takes you forever to stay in the transient, right? Because you are 200 dB away from target. It would take you forever to reach the new target, right? So if your initial dynamic range without open loop power control, the initial dynamic range can be 200 dB off the target, then you are bound to use a large delta. And then you are bound to suffer from extra large steady state error due to the large delta. Is that okay? So therefore, but now with the open loop power control, it neutralizes the path loss, neutralizes the shadowing. So the remaining dynamic range will be just around 30 dB. So that means your initial measurement could be just 30 dB away from target, much smaller. And this allows you to use a smaller delta. Understand the mechanism? So that's why open loop power control also play an important role. It's not just you just dump everything to closed loop. Okay? Closed loop, it allows the closed loop to use a smaller delta so that you have a smaller steady state error. Is that okay? Now, this is one frame in IS-95. One frame is 20 milliseconds. So after one frame, you are allowed to update the target. The target can be adjustable. You can update the target. So in this example, the target is updated to here. So you have another transient. So in this case, the actual measurement is below the new target. Okay? So you keep on increasing delta until you reach the steady state of the new target. Is that okay? So this is undesirable because here, if you stay in this transient for a long time, you create excessive interference and you will jeopardize the capacity for random CDMA. Here, if you stay in this transient for too long, your call may be dropped because the uplink traffic channel will have extra high error probability. Okay, so you may have extra core drop rate. Okay, so this is very simple inner loop power control. Yes, what else do I want to say? Right, okay, I forgot, actually. Never mind, so this is inner loop power control, okay? Okay. Now, what about outer loop power control? Now, outer loop power control, now inner loop power control is done at the base station side. Okay? Now, what about outer loop power control? Again, we try to understand this using a black box approach. It has two inputs. The first one is the frame error rate target. Okay? You want to have a certain target frame error rate. And this target is determined by the application. For example, if this is IS-95 for voice application, typical target is 1% frame error rate. That means on average, you lose 1 frame out of 100 frames, that will be okay. If you go below 1%, the speech quality won't be noticeable, okay, due to the nature of the speech encoder and decoder. So operating at 1% is the target, is the optimal frame error rate target. Now if you change to video streaming, the video encoder, video codec may demand another target, and typical video codec will have a frame error rate target of 0.1%. Okay? The point here is this target is fixed by the application. So this is one input. The other input is the actual frame error rate. We are always talking about the uplink traffic channel. Okay, the frame error rate of uplink traffic channel. So with these two inputs, you compare the actual frame error rate with the target, right? The idea, the output is what? The output is SIR target. This SIR target is used to drive. So this is connected to here. It's to use to drive the target for the inner loop power control. Okay? So the analogy is like, this is like a manager. This is like a salesperson. So once every 20 milliseconds, once every frame, the manager will dispatch a new sales target to this sales guy, and this sales guy, through this inner power control, is trying to meet this sales target on a frame-by-frame basis. And after 1 frame, the manager can pass you, can update the sales target, just like this. This is the initial target for 1 frame, frame number 1, and then this is the SIL target for frame number 2. Okay? Now, so how do you drive the target? The idea is, again, very simple. If you see that the actual frame error rate in the uplink traffic channel right now is better than 1%, then what do? So you increase the target or decrease the target? If the actual frame error rate is better than 1%. If it's better than 1%, you should decrease your target. Why? If the actual frame error rate is better than 1%, that means the mobile is transmitting more than what it is needed, right? If the mobile is transmitting more than what it is needed, it is undesirable because it will generate excessive interference to the others. So in random CDMA, you always try your best to keep the interference level as low as possible. That means you always try your best to avoid unnecessary transmission. Okay? So therefore, if the actual frame error rate is better than 1%, then you should decrease your target. Right? On the other hand, if the actual frame error rate is worse than 1%, that means the mobile transmission power is not sufficient, right, to maintain this target frame error rate. Then in that case, you should increase your target. Is that okay? So that's kind of the adjustment. Is that okay? And this is updated once every 20 milliseconds. So this is slower. So this is what we call 50 hertz. Over 1 second, you can only update this SIL target 50 times. Okay? Now, however, this is just a conceptual diagram. This is not something implementable. What do I mean? Now, okay, let me describe the other. Let me start over again. In previous chapter, we say that there is always a bit error rate curve, right? And this is SIR in dB. This is in log scale. So let's say you have a IS-95 transmitter and receiver data path design, okay? And based on that, so let's say you know what the transmitter is trying to do, what modulation, spreading, and then the demodulator, despreading, demodulator. So everything is fully specified for you. And let's say I ask you to write a simulation program to generate, with a simulation, you can generate a bit error rate curve like this, right? We keep on talking about this curve for a long time, correct? Now, once you have this error probability curve, then I need a 1% target, right? So this is my 1% target. From this frame error rate curve, from this error probability curve, I can read from this curve that maybe I need 10 dB as my SIL target. Then I do this offline. So I figure out I need 10 dB SIL target. And then I fix this SIL target to be 10 dB all the time. If I do it this way, I won't need this out-of-loop power control, right? So my question is, why do I need this out-of-loop power control if I can do it offline? So this is an offline approach. This is an online approach. This is online because you dynamically try to learn what should be the target, what should be the correct target to achieve 1% target error probability, right? So this is done online. But why do we need to do it online? Why can't we do it offline? What's wrong with this offline approach? Is it possible to do it this way? Let me go through the logic again. Let's say I give you the specification for the transmitter and receiver. Okay? I specify everything. How do you do encoding, modulation, how do you do spreading, how do you do despreading, demodulation, etc. And then I ask you to simulate this curve. So you can write the MATLAB simulation to simulate the frame error rate, right, versus SIL. And then based on this simulated curve, I can read from this to achieve 1% frame error rate target. I need 10 dB. And then I always fix this to be 10 dB. Understand the plan? What's wrong with this? What's wrong with this offline plan? Anyone? Why this is not realistic? Very simple, right? Back to day one. If you still remember what I talked about in day one in the first lecture, I said that what I said is before you attempt to design a transmitter and receiver, right, you must know the channel. That's the first thing you should worry about, right? So if I just give you a transmitter spec, receiver spec, and ask you to simulate this curve, are you able to simulate this curve? No, because you don't know the channel, right? Now, the question is, we'll talk about this, right? If this is additive wide Gaussian noise channel, you get one curve, right? If this is flat fading channel, you get another curve, right? So the curve depends on the channel. But this channel is between the base station and the mobile station, between the mobile station and the base station. And this channel, is it something you can determine offline? No, right? Because that depends on where you are. So in a conversation, you can be here, you can start a call in the room. And then after you're talking to your friend, you leave this room and go to the piazza, right? So the channel, the environment keep on changing. So it is not possible to simulate a line like this offline. And that's why you need an online learning loop. This is an online learning loop to learn the mapping from frame error rate to SIL target. Is that okay? So that's why this is not feasible, because you don't know what will be the channel between the mobile and the base station. And the channel will keep on changing. Okay, so this is an online mechanism. You need to online learn the mapping from the frame error rate to the SIL target. And that's why this needs to be adjusted dynamically on an every frame by frame basis. You need to update the target every frame because the channel keep on changing. All right? So that's number one question. Number two question is, okay, what about this? Can we implement this? I just mentioned this is just a conceptual block diagram, but it cannot be implemented. What's wrong? Why you cannot implement this out-of-loop power control in this way? Now the question I'm asking you is, always try to develop the mindfulness from an equation or from a conceptual algorithm to implementation, right? So I'm trying to train you to be an architect. You always get to be a good architect, you need to have this kind of mindfulness. When you see something, you need to be alert of the potential implementation challenges. So what's the implementation challenges? If your system engineer tells you about the scheme, why this cannot be implemented this way? What's wrong? Now to go through these 3 parts, right? So this guy, frame array target is just a fixed number. It's not a problem, right? So for voice application, it's fixed to be 1%, 0.01. Okay, so this is a fixed number. So no problem, right? What about this? Can you measure the actual frame error rate? How do you measure the actual frame error rate? What is frame error rate? What's the definition of frame error rate? The numerator is the number of frames corrupted, right? The denominator is what? Total number of frames transmitted, right? This gives you the frame error rate. That's the definition, right? Okay. Now, in practice, if I'm trying to measure the frame error rate of the order of 1%, how many frames do you need to observe? Can you observe 1 frame and tell whether the frame error rate is 0.01? No, right? How many frames do you need to observe? If you observe 100 frames in the denominator, so on average, the numerator would be 1, sometimes 0, sometimes 1. But that is not that reliable, right? If you are trying to measure to the order of 1%, the denominator cannot be 100, right? Now, so your rule of thumb is usually 10 times, okay? So denominator, if the denominator is 1,000 frames, then the numerator on average will be 10, sometimes 9, sometimes 11, right? So then the estimation would be reliable up to this level, right? So then what's wrong? How long it takes you to measure 1,000 frames? 1 frame is 20 milliseconds. 1,000 frames is 20 seconds. So if you try to measure the actual frame error rate now, if you use this brute force approach, you will get this a reliable estimate only 20 seconds later. Now 20 seconds later, you get this measurement. Is it going to be useful? Of course not, right? It's 20 seconds, it's very outdated. Okay? So this is just a conceptual diagram, but this cannot be implemented in this way. And at that time, but this is playing a very important role. Because if you're doing a poor job, that means your target is incorrectly set. Either the target is too high. If the target is too high, that means in your infrastructure, most of the mobile will transmit excessive power, and therefore the capacity will be jeopardized. Your capacity will be smaller than your competitors. If this target is very conservative, right, then that means this target is too low. That means your mobile station will always transmit below what is needed. And then in your system, you have lots of call drop compared to your competitors. Okay, so this out-of-loop power control, how you do a good job, is critical to the performance of your CDMA network. And this is something nice because this is very important on one hand. On the other hand, you cannot implement in a brute force way like this because this is the technical barrier. Okay, how do you make a real-time measurement for this frame error rate is the critical barrier, is the challenge. And this is an ideal situation for innovation. So at that time, lots of CDMA vendors. So at that time, I worked in Bell Labs, and I was working on that part. And so different vendors will have different innovations and these key patterns to get over this problem and have a real-time measurement. So now, of course, I'm not going to go into the details of this, but this is just to let you appreciate. This is some good configuration that is critical block, but it cannot be implemented in a naive way. So if you can get over this challenge, that will be a good problem to have innovations. Now I'm just telling you one example to bypass this, but this is also not a good implementation. In fact, most of the vendors is using this baseline scheme as a baseline. So we try to do something better than this. But let me explain this toy example as a baseline. So how do we do how do we do outer loop power control without explicit measurement of this guy? So the idea is pretty interesting. So this is the SIR target in the uplink. This is time. So what the base station ultimate power control will do is like this. So let's say this is the initial target. Okay. So if there is no frame errors in the uplink, remember in uplink traffic frame, every frame has CRC check. So base station as a receiver will know whether this frame is correctly received or not by checking the checksum CRC. So if there is no frame errors, then the base station, the ultimate power control will try to decrease by a parameter called dan. This is a parameter. Decrease the target by a certain parameter dan. If there is no problem, no frame errors, you keep on decreasing. You keep on doing this until you start to see 2 frame errors. If you start to see 2 frame errors, then you increase the target by another parameter called up. Okay? And after you increase by up, you have no problem again. So you start to decrease again. So it will be like periodic. Is that okay? The steady state is like periodic. Now the way to understand this design philosophy is I call this a bullying cycle. Because the mechanism is very similar to how you bully a person. I'm not telling you how to bully a person. I'm not teaching you how to do it. But that's how, if you observe, right, how people bully each other is like this. So suppose A try to bully B. So usually A will try to push the boundary a little bit, right? If the victim didn't complain, then you will keep on pushing the boundary a little bit further, right? Bit by bit every time. Until the victim try to cry out, okay? Try to react violently. Then this bully will step back, right? And then start all over again. So this is the bullying cycle. Is that okay? So nothing happened, you keep on pushing the boundary until you start to see problems, frame errors. And then you back up by another parameter and you start this again, testing the boundary again. Okay, now in this case, now in the entire process, there is no explicit measurement of this frame error rate, right? So that doesn't involve explicit measurement of frame error rate. So in this case, how do you maintain a certain target frame error rate? So the way is like this. You can think of that as a periodic cycle. So this is one period. In this one period, how many, so on average, in one period, there are 2 frame errors, right? So the frame error rate is, average frame error rate is 2 corrupted frames over the number of transmitted frame on one period, right? So what is the number of transmitted frame? This is up. This is down, right? So by simple math, the number of transmitted frame is up divided by down. Is that okay? So this will give you the average frame error rate. If I want this to be 1%, then this will give me a guideline for up over down. Okay, so in this case, down over up. These 2 parameters this ratio should be what? 0.005. Is that okay? By setting these parameters to this ratio, then the average frame error rate will be 1% using this bully cycle mechanism. Okay? Now, but I say that this is not a good design because here you achieve 1% on average. So the average frame error rate is 1%. But if you look across this design, you are always oscillating between 2 transients. Here, during this transient, the mobile is transmitting more than what it is needed, right? So it will cause excessive interference to the others. Here, the mobile is not transmitting sufficient, okay? So you are oscillating between these 2 types of transient all the time. Although on average you have 1% frame error rate, but this is not it's not very good, okay? So that's why we always just use that as a baseline, and people can do better than this. The key is, are you able to get a real-time measurement for this frame error rate, okay? And there are some technical details which I will skip. So if you're interested in that, you can search the pattern, outer loop power control for CDMA systems. There are quite a lot of different patterns. Okay, so anyway, so this is a combined picture, integrating the open loop, closed loop, inner loop, and outer loop, okay? So you can see that, let's say in this scenario, this is a base station, this is a mobile station, and there's a blockage by building. So initially, mobile station have a line of sight with the base station. So the RSSI received by the mobile station is pretty high. Okay? So as the mobile moves towards the base station like this, it's gradually entering into the shadow of the building. When it enters the shadow, you have a sudden drop of the RSSI. In response to this sudden drop, you see a sudden increase in the mobile transmit power here. So mobile transmit power suddenly increased here. Okay? Now, before you enter the shadow, you see, look at the base station SIR target, okay, in the uplink traffic channel. So this is the target, the dotted line is the target. And then the solid line is the receive SIR. So you see that this is in the steady state. Okay, so far so good in the steady state. And the signature for steady state is you observe the base station power control command. It's alternating between plus and minus, plus and minus. So that will be the signature for steady state. Okay? Now, when the mobile enters into the shadow, so you have a blockage, suddenly the receive power will be dropped. So suddenly the uplink traffic channel receive power also drop below the target. So now what happens is, due to the action of inner loop power control, the mobile transmit power is increased by delta, increased by delta, increased by delta. So this is a transient. Okay? So you can also see the signature of transient by observing the power control command being plus, 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 consecutive plus. This is an indication of a transient. Okay? So after it reached the new target, then it reached the steady state again. So far so good. So steady state, again, you see the power control command alternating between plus and minus, plus and minus. Okay? And now after a while, the mobile leaves the shadow and have line of sight with the base station again. So when you leave the shadow, you don't have blockage. So the receive power suddenly increase. And that's why the uplink traffic channel receive power also suddenly increase above the target. So then base station power control command will be consecutive minus, minus, minus. So mobile transmit power in response to that decrease the transmission power by delta by delta. So this is the up transient. Okay? During this transient, the mobile is transmitting more than what it is needed. Is that okay? So after some time, it reached the new steady state again. Okay? So this is the change of mobile transmit power. This is a combined action between open loop power control and closed loop power control. Is that okay? So if you work for operator, how do you know you are in a transient or not? You look at the base station transmit power control command. Okay? If the power control command is alternating between plus and minus like this, then you know this is in steady state. If you see a large window of consecutive plus or consecutive minus power control command, then you will see your system operate mostly in transient. Okay? Any questions? So this is a reverse link power control. All right? Now, so every CDMA system, in order to understand every CDMA system, you need to understand the power control. Okay? So power control is not just saving your battery power, it's to save your capacity for random CDMA. All right? Now the third important component is handover, in particular soft handover. Now what do we mean by handover? Now remember, when we have cellular architecture, the coverage area is now partitioned into many small coverage area by every single base station. The purpose of doing that is you want to scale up the capacity by frequency reuse, right? Or by resource reuse. But the price you have to pay is, since now the coverage area is not contiguous, it's partitioned into many base stations. So when you start the phone call in one location and you're in a traffic conversation state with the traffic channel assigned to you, and then you keep on moving, right? You can cross the cell boundary. When you cross the cell boundary, you don't want the call to be interrupted by this mobility. So that's why you need to have some built-in mechanism for smooth handover. Smooth handover means, although you cross the cell boundary, this cell boundary crossing should be transparent to the user. The user should just keep on talking without even aware of this boundary crossing. Is that okay? Now to make sure this, then that means how do you ensure this smooth handover without attention of the user? Then that means there are some signaling component behind the scene between the mobile and the base station in order to facilitate handover. So this is the topic of handover. Okay, so handover is the process of transferring the call when mobile station move out of the coverage of one base station and enter into the new coverage of another base station. Now there are two types of handover. One is called hard handover. Hard handover, like GSM, this kind of system is what we call break before make. That means when you leave the old base station, you have to terminate the connection first before you establish a new connection to the new base station. So that means there will be some time that you are not connected to any base station in the process, although that is very short, usually within a few hundred milliseconds, that should be completed. Okay? That's called hard handover. The keyword is break before make. But CDMA also has a unique advantage of supporting something called soft handover. That is make before break. That means before you leave the old base station, while you still have the old connection, the handover process allows you to establish new connection with the potential new base station, so that when you leave the boundary, you will not have any time that are unconnected. Okay? If you are still confused, this is just think about your daily life. Suppose after a while you want to change jobs. If you want to change job, would you like to do hard handover or soft handover? Hard handover means you quit, submit a resignation letter without knowing where you would go. Okay? So this is there's a term for this. This is in Cantonese it's called 裸辭. So you just quit without finding a new job. I don't know how to pronounce it in Mandarin, but never mind. But what you would like to do is also actually soft handover, right? That means before you submit the resignation letter, you probably want to have an offer for the new job before you submit the resignation letter, right? So that is called soft handover. So in CDMA network, it allows more reliable handover by allowing something called soft handover. Now with soft handover, that means you will have some brief period of time that are talking to more than one base station. Okay, so I will explain that in a minute. Now, no matter you are doing hard handover or soft handover, the important concept is the handover decision or execution is done at the base station controller, not even at the base station. It's at the base station controller. Mobile station just play the role as assisting the base station controller to make the decision. The decision is not made by the mobile station. Okay, so mobile station just supply the base station controller with essential information so that the base station controller can make the decision and execute the handover. This is very different from Wi-Fi. For Wi-Fi, the handover execution is locally at the device, okay, not at the access point. But for cellular system, the execution has to be in the infrastructure, base station controller, for some reason, okay? Now, okay, so let's look at, so how do you design a handover algorithm? Now, for handover, there are several things you need to tell. The first thing is when to do handover. What should be the timing? The timing is very important. Okay, so you are the mobile station. You blindfold yourself. You are assigned with a traffic channel by a certain base station. So how do you know you are leaving the base station? How do you know you are leaving the base station? You are blindfolded. Obviously, the only thing you can rely on is the pilot channel, right? The base station keep on transmitting certain pilot channel. So one reference is you can measure the pilot channel strength, pilot channel strength from the base station. Now, if this is your base station A, pilot, and you observe that base station A pilot is like this, what does that mean? That is a strong signature that you are leaving the home base station, right? Because the pilot strength from the base station is getting weaker and weaker. This is like I'm the base station, I keep on transmitting a pilot channel with a constant power. And you blindfold yourself, you're walking around. If you hear my pilot channel power weaker and weaker, that means you are leaving me, right? You're moving away from me, right? So by monitoring the base station for the home cell, let's say your home cell is A, then you will be able to tell when should you engage in handover. But engaging in handover is more than this, right? The second question you want to find out is where to hand over. Where is the new base station? Now you just know you're leaving the home cell. That's not helpful, right? you need to, for the base station controller to handle the handover execution, the base station controller also need to know who is the new cell, right? So how do you know who is the new cell? Again, the only thing you can rely on is the pilot strength, right? So every base station, even your neighboring base station, will be broadcasting the pilot channel. So the mobile station has to, if the mobile station can measure the pilot strength of the home base station as well as all the neighboring base station. If you see some profile like this is the pilot strength of base station B, and then this is the pilot strength of base station C. Then what does that mean? So this is a strong signature that suggests you are leaving home cell A and entering into base station C. Is that okay? So therefore, these two questions will be answered by the mobile station through monitoring of the base station, through monitoring of the pilot channel strength transmitted by not just the home base station but also the neighboring base stations. So mobile station is very busy. Mobile station on one hand is handling the traffic channel, decoding the speech, right, for between the user and the infrastructure. But at the same time, the mobile station has to keep on monitoring the pilot strength of all these base stations. Okay, not just your home base station, but also the other base station. Okay, so, but of course, you think of the mobile station as a computer, as a small computer. So each time you measure it, you consume some computing power. Okay, so you cannot, with limited computation power, you cannot measure all the pilot channel at all time. You need to achieve a careful balance between how frequent you sample the pilot channel and how many pilot channel you monitor. Okay, because you have a fixed total computation power. So the handover algorithm is trying to exercise this trade-off. So you need to differentiate on one hand, which base station are more important, which base station are less important. Now, what do I mean by more important? For example, if this is a base station A, this is your home base station. This is your mobile. Okay. Now, if base station B, base station C, they are your topological neighbor, then of course, to this mobile station, these topological neighbors will be more important. They should deserve higher priority than the other tiers, right? If this is base station D, base station D would have less priority, right? Because it's not an immediate neighbors. So how the mobile station know which are the neighbors, topological neighbors? Remember last time, in the paging channel. In the paging channel, there is one message broadcast by the paging channel called neighbor list message. This neighbor list message will broadcast the topological neighbor. So this base station A will broadcast the neighbor list message. In this neighbor list message, it will list base station B, C, E, whatever are the topological neighbors. So through receiving this neighbor list message, when the mobile is in idle state, the mobile will know who are the topological neighbors. Okay. Back to this. Okay, so now the handover algorithm is divided into the mobile side and the base station controller side. As I said, the decision or the execution is not at the mobile station side, but mobile station plays a critical role because only the mobile station knows when to do handover and where to hand over to. So base station controller wouldn't know. So the base station controller, in order to make a decision, it has to rely on the mobile station to report a timely measurement or timely events. Okay? So the role of a handover algorithm in mobile station is to detect what we call a handover event. There are three types of events. One is called add event. The other is called drop event. The third type is called swap event. I'm going to explain this. So the whole mobile handover algorithm is from time to time is a forever loop. This loop keep on monitoring any of these events. When any of this event happens, it has to inform the base station controller through the base station. Okay? So there will be explicit signaling by mobile station to the base station controller when any of these events happen. Now, to explain this event, I need to first define some terminology. So in IS-95, the base stations are divided into 4 sets. The first one is called active set. The active set contains the base station that are involved in delivering traffic frames to the mobile station. So this is, in roughly speaking, these are the base stations that are connected to the mobile. So mobile can expect traffic frames coming from these base stations in the active set. Now, because you allow soft handover, so that means the base station in the active set can be more than one. Okay? Because at some time you can simultaneously talk to your old home cell and the new base station simultaneously, right? Soft handover, you make before break, right? So the active set can have more than one member. So the standard allows 6, maximum entry of 6, but in reality, most of the time, the active set members will be 2, at most 3, okay? For some reason, which we are going to explain. Now, so this is the active set. Any change of membership in the active set must involve base station controller execution. Mobile station cannot on its own change the membership, okay? So that is what we call handover execution. The handover execution involves change of membership of the active set. Okay? So it must be done at the base station controller side. Now the other set is local at the mobile station. So they are just defined with different priorities. Candidate sets are those base stations with very important base station. This base station in the candidate set, they are potential base station to be promoted to the active set. Okay? So they're high priority base station. Neighbor set, those are the base stations that are topological neighbors. Okay? Topological neighbors. Remaining sets are just the remaining other base stations. Okay? So these are the 4 sets of so-called pilots or base stations. Now let's look at the handover algorithm for mobile station. Now, as I said, it's a forever loop. In this loop, the mobile station keep on finding this add events, drop event, and swap event. When any of these things happen, the mobile will report to the base station controller through some signaling message, which we are going to explain. Now, what do we mean by add event? Add event is the event when mobile station finds a strong base station and it wants to add to the active set. Okay? So that would be called add event. That means you find a strong base station, you want to connect to this strong base station. You want to add this into the active set. Drop event is the opposite. Now, by definition, members in the active set must be strong base station. Okay? But as you are moving, so when you promote some base station into the active set, it must be strong. But since you are moving, there could be some base station in your active set that becomes weak. If this becomes weak base station, you want to kick them out of the active set. So if you want to kick out someone from the active set, this is called a drop event. Now swap event is just a combine of add event and drop event together. You want to swap, you want to drop one out of the active set and then replace with another base station into the active set. Okay? You just combine add and drop together. Okay, so let's look at how mobile station monitor and detect for this add event, drop event, and swap event. So remember, similar to power control, you need to worry about handover algorithm only when you are in conversational state. That is only when you have traffic channel set up for you. Okay? If you do not have traffic channel, if you're in idle state, then the handover is just by yourself. Okay? There is no need for handover decision, no need for handover execution. Okay? So this is the starting point. You are in conversation state. Now, what you do is at a mobile station, you try to measure the pilot strength of all active base stations. So all the base stations in the active set, you try to monitor the pilot strength. And then you measure the pilot strength on all the base stations on your neighbor set. Okay? Now, if you find any base station in the neighbor set with a pilot strength larger than a threshold called T@, okay, then you call this a strong base station. If you find any strong base station, you want to promote this to the candidate set, okay, promote this strong base station to the candidate set, and then you send a signaling message to inform the handover, to inform the base station controller. I will explain this message. This is called pilot strength measurement message. In short, we call this PSMM, okay, pilot strength measurement message. This is sent by the mobile station to the base station controller through the base station. Okay? So now you see that this is add event. When you detect some strong base station, what do you mean by strong base station? The pilot strength larger than the threshold called T@. Then you promote it to the candidate set, and then you send PSMM message. In the PSMM message, you will say, I want to promote this base station to the active set. Okay? Now, if nothing happens, you didn't find any strong base station, you move on. Okay? You try to measure the signal strength of all remaining pilots, the pilots in the remaining set, which are lower priority. Again, you try to look for any strong base station.
What do we mean by strong base station? The pilot strength larger than T@. If you find any strong base station in the remaining set, you do the same. You promote this to the candidate set and you inform the base station controller by sending PSMM message. These two are the add event. Okay. Now about the swap event. Now you measure the candidate base station. If you see any candidate base station pilot strength larger than the active base station pilot strength, then you send a PSMM message suggesting a swap. Okay. Swap is I want to kick out this weak guy in the active base station and replace with the candidate base station. So this is a swap event. Okay. Now if nothing happened, the remaining thing is you look for drop event. So you want to kick out those active base stations that are weak. Okay. Now what do we mean by weak? You check for two conditions. Any active base station with the pilot strength less than another threshold called T drop. Now if there is some active base station less than T drop, then you start a timer. You don't do anything at this point. You start a timer. If this weak condition lasts longer than another timer called TT drop, then you take action. You take action by sending PSMM message. In this message, you will put down, I want to kick out this base station from the active set. So this is a drop event. Is that okay? And this will be looping forever. So that is essentially the mobile handover algorithm, trying to identify each one of these events. Now, because without the mobile station, the base station controller will have no way to know when this event happened. Now, if you do not do a good job in the mobile station, if you miss this event, then the call may be dropped. If, let's say, you are moving from the home base station, but you missed this handover opportunity, you didn't catch this add event, then by the time you notify the base station controller, it may be too late already, because the signal connection from your home base station may be too weak. And then in this case, your call will be dropped. Okay? So it is very important that you maintain a timely measurement in order to identify this event instantaneously. Okay? Now let's look at one example. Now this is a simple example like this. You have a base station A and base station B. Mobile is connected to the base station A. So base station A is the mobile's active set member during the beginning. And then mobile station is moving away and gradually turn back. So this is a toy example with this trajectory. So if you look at the active set, okay, so active set initially is base station A. Okay, and then gradually, and the neighbor set initially is base station B. So that's the starting configuration. Okay. Now the mobile is running this handover algorithm. Okay. From time to time, it's trying to identify add event and drop event, right? So let's say this is the pilot strength of base station B. So initially, base station B is very weak because mobile is here. So base station B is very far away. So pilot strength from base station B is very weak. So nothing happened. But then as the mobile moves towards base station B, this pilot strength from base station B keep on increasing, right? Meaning mobile is moving towards base station B. Now, nothing happened until at T1. At T1, what happened? This base station B in the neighbor set has a pilot strength exceeding T@, right? When it exceeds T@, this is regarded as a strong base station. So base station B is doing T1. Base station B is a strong base station. So the mobile wants to promote this guy to the active set. But mobile cannot do it on its own. So it has to send a PSMM message signifying to the base station controller that I want to add B to my active set. Okay, so this is an add event. Now, base station, so it should be the base station controller, not base station. Base station controller, in response to this, it will try to approve this handover request and execute the handover. I will explain what we mean by execute. And after that, after everything is set up properly, base station controller will send a handoff direction message. This is a downlink signaling message to the base station, to the mobile station. Okay, so at T2, indicating that the setup is complete, and then the mobile station has to respond acknowledgement with a handoff completion message back to the base station controller. So this three-way handshaking is used to confirm a handover event. So this handover event in this example is an add event. Is that okay? So at T3, so at T1, base station B will be promoted from neighbor set to the candidate set locally at the mobile station, just like this, right? When you see a strong base station, you promote this to the candidate set, and then you send PSNM message. Okay, so at T1, mobile will move base station B from neighbor set to candidate set. At T3, the handover execution is completed. So base station B is now promoted from candidate set to active set. So from T3 onwards, the active set consists of A and B together. And we say that this mobile is in soft handover from T3. Is that okay? Because from T3, this mobile is talking to two base stations simultaneously. Okay? Now, so far so good, right? So base station B and A now is in the active set. Okay? But as we said, right, you want to make sure that the active set only consists of strong base station only. Okay? But now, as the mobile moves away from base station B, like this, so you see that the pilot strength of base station B is decreasing, right? So nothing happened until at this point, T4. At T4, what happened? This base station B and active set member have the signal strength drop below T drop. Okay? Now, drop below T drop, the mobile station, according to this algorithm, it won't take any concrete action yet. It will start a timer and make sure that this condition lasts for a timer longer than TT drop. So you will start a timer. If this condition, like this example, lasts longer than TT drop, then at T5, the mobile station confirms this is a drop event, and it will start to take action by sending PSNM message to the base station controller. The same signaling message, but in this case, the mobile will fill up the form in this message, saying that I want to drop base station B from my active set. Okay, I want to kick out base station B, essentially. Okay. Now, base station controller receiving this message via the base station, it will try to approve this request and then carry out the execution. After the execution is completed, base station controller will send via the base station a handoff direction message to the mobile station, and mobile station will respond with a handoff completion message to finish the configuration. At T7, base station B will be kicked out from active set back to the neighbor set. Is that okay? So this example illustrates an add event and a drop event. So when are the time that mobile engage in soft handover? From T3 to T7. Because from T3 to T7, the active set contains base station A and B together. From T7 onwards, the active set only contains base station A. And before T1, the active set also consists of base station A only. Is that clear? So that's the soft handover. Okay? Now, so that is what the mobile is trying to do. From time to time, it always tries to identify add event, drop event, or swap event. It must be identified on a timely basis, because if this mobile station misses this add event, then the mobile station will be moving deep into the base station B. And then the original connection may become very weak. And then the base station will keep on receiving traffic frame errors. And then the link will be dropped. The call will be dropped. Okay? So missing a single handover can result in call drop. So it's very important that you have identified this potential add event on a timely basis. Now, okay, I explain how it works. Let me try to briefly explain why it's designed in this way. Now, you notice that in the add event and drop event, the treatment are a little bit different, right? In the add event, the mobile station, upon the pilot strength larger than TAD, it will take immediate action to add it, right? To send PSNM message and promote this to active set. But for the drop event, when this guy pilot strength dropped below T drop, it didn't take immediate action, right? It tried to be more careful by giving it another chance to make sure that this weak condition lasts longer than a certain time before you take action, right? Can you see that? So there's a different treatment. Why? Why you need a different treatment? When you do add, you tend to be more aggressive. When you do drop, you tend to be more careful. Why? Well, this is, again, a common sense. If you think in a higher level context, this is, I guess, a basic decision-making theory. If you have to make a decision, there are certain chances that you'll make an incorrect decision, right? You can make a mistake on every single decision. Let's say we talk about binary decision, okay? Well, suppose somebody offer you a game, a gamble game. If you make the correct decision, they will give you $10 in reward. But if you make a wrong decision, they will take your life. Now, let's say you don't have a choice, you have to participate in this game. And in this case, would you be very aggressive in making a decision, or would you try to be more cautious? You tend to be more careful, right? Because the penalty for a mistake is very huge, right? So, on the other hand, if the game is like, if you win, if you make a correct decision, you try to guess something. If you guess it correctly, I give you $10. If you guess it wrongly, I deduct $5 from you, right? But in that case, what would you do? What would be your strategy? You try to be more aggressive, right? It's the same idea. Now, in the ad event, now in every case, you want to promote some guy into the active set, thinking that this is a strong base station. But you don't want to promote a base station simply because of fading transient. You want to promote the base station, you think this is strong, you want to promote it, you want that strong to be strong due to path loss reason, not due to fading transient, right? But you never know. You can only rely on the measurement. And this measurement, this is an ideal example, but in practice, the measurement fluctuate up and down, right? So you think this is a strong base station, but you have a certain chance of making a mistake. You may promote a weak base station, but this appears to be strong due to occasional fading transient, right? So in this case, you may make a mistake. Now think about if you make a mistake. You promote a weak base station into the active set. What will be the problem? Well, if you promote a weak guy into the active set, at least your active set still have a strong member, right? Base station A is still strong, right? So your call is still okay. You just promote a useless base station into the active set, you waste a bit of resource, right? But overall, the call will still be maintained. There won't be any danger to a call drop, right? On the other hand, in a drop event, if you drop you want your original intention, if you want to kick out a weak base station from the active set, right? But if you make a mistake, you may kick out a strong base station from the active set, right? Now, if you really kick out a strong base station from the active set, what will be the consequence? That means the active set will now be containing weak base station only. That means your call will be now supported by weak base station far away from you. And that means you have a high chance that the call will be dropped. The consequence will be high. Is that okay? So in the ad event, the consequence of a mistake is relatively mild. But in a drop event, the consequence of making a mistake is heavy because that means the call may be dropped. Okay? So because of that, just like the common sense, for decision involving more severe consequence for making a mistake, you tend to be more careful, right? So that's why for ad event, you tend to be more aggressive. You take immediate action as soon as you find this is strong. But for drop event, you tend to be more careful because if you falsely drop out a strong base station from the active set, then the call will have high chance being dropped. So you tend to be more careful. Is that okay? So I hope you understand. All right, so this is the mobile handover algorithm. What about the base station controller? Base station controller. Now to explain the base station controller, let me use this picture. Toy example configuration to illustrate the idea. So now, the mobile station is here. And then the base station is connected to the base station controller. Like this. Now initially, the base station A is the active set members for the UE. So the traffic channel will come from base station A, right? So let's say in the downlink, the traffic channel will be coming from base station A. Let's say this is on W60. Remember, downlink is operating on deterministic CDMA, right? So every traffic channel has a wash code or orthogonal codes to spread the data, right? So, and then the traffic, so let's say this is the mobile switching center. The speech frame will be coming from mobile switching center into base station controller, and the base station controller will deliver the traffic frame through this backhaul. This is a backhaul, usually a T1. A T1 have 24 channels, okay? So deliver through the backhaul to the base station, and base station deliver the traffic frame to the mobile. It would be like this, right? When you during the initial period like this, okay, before T1. Now let's say at T1, this base station controller received a PSIR message from this mobile station asking, suggesting we should add base station B into the active set, right? So of course there is a reason. The base station controller would of course trust the request by the mobile station, so it will approve this request whenever possible. But still, base station controller needs to check for two things. Number one, it needs to check if there is any spare capacity in this backhaul. It could happen that this backhaul is fully occupied because this base station will have its own local subscribers, right? It could happen that this base station B is fully loaded. Then all these backhaul channels is used up. It could happen this way, right? So number one, base station controller needs to, before you can add base station B into the active set, it needs to check whether this is available. Number two, it needs to check whether the radio interface has available downlink channels. Okay? So if these two are yes, then of course the base station controller will approve the request. But what do we mean by approve the request? The next step is you have to go through the execution. What do we mean by execution? When base station B is added into the active set of mobile, that means the traffic frame has to come from base station B as well, right? And that means the base station controller will need to deliver the speech packet, the same speech packet to both base station A and base station B. So that's why it involves a backhaul capacity. It also involves a radio interface channel. Okay? Now if the loading is permitted, then base station controller will set up the backhaul, will set up both station controller will set. In this handoff direction message, it will also tell the mobile station what is the watch channel. For example, this is W50. This does not have to be the same as this. Okay? So on the base station B, it may be spread using W50. So W50 will be delivered to the mobile station through this handoff direction message as well. So mobile will know the despreading sequence for the traffic channel coming from base station B. Okay? So this is a downlink direction. So that's why the execution cannot be done at the mobile station, because mobile station has no way to know the resource of the target station and no way to set up the backhaul resource for the new base station as well. So the execution must be done at the base station controller. Is that okay? So now this is a downlink direction. Now what about the uplink direction? The uplink direction is similar. So when you have this soft handover arrangement, the mobile station in the uplink will send the broken pieces simultaneously over the air, right? And then the base station A and base station B will pick up the uplink broken pieces, okay? So base station A will try to decode the frame and then deliver to the base station controller. Base station B will also try to decode the frame and then send to the base station controller. So base station controller on the uplink will receive two copies of this traffic frame, right? Decoded by base station A and base station B. So inside the base station controller, there is a frame selector. This frame selector will select a good frame from these two input frames to the mobile switching center. Is that okay? So two base stations in the active set will deliver their decoded copies of the frame to the frame selector. So some may be good, some may be bad. But it doesn't matter. The frame selector will just need to select a good frames from these two frames, two decoded frames. As long as this is good, then this is happy. Okay? So that's the uplink direction. So that's why when you engage in soft handover, if you work for operator, when you dimension the number of channels needed in a base station and the number of channels needed in the backhaul, you don't just, no. So this is unique to CDMA network. If this is a GSM network, there won't be any soft possibilities. So when you dimension a base station in terms of number of channels and backhaul capacity, you just need to dimension it properly according to the potential subscribers, according to the subscriber loading. And based on the subscriber loading, you can determine how many channels, how many time slots do I need to provision, and how large the number of backhaul do I need it, okay? But for CDMA, because of soft handover, okay? Now you can see that soft handover is not free. With this example, if you have this two-way soft handover, to support one call, you need double the radio resource and also double the backhaul resource, right? If you have no soft handover, to support one guy, you just need one radio interface channel, also one backhaul channel. But now with soft handover, two-way soft handover, to support one call, you need two radio channel. You need two backhaul channels. Is that okay? So you double the resource required. So when you dimension, if you work for operator, when you try to figure out how many channels you need for a base station and how many backhaul channels do you need to account for not just new subscribers, but you also need to account for potential handover requests. Okay? So that's why if you, on average, you have 10 new subscribers, okay? But then you have 5 handover requests, then the total dimensioning capacity should be 15 instead of 10. So that's my point, okay? So handover is not free. So that's why I said earlier on, in the standard, the maximum entries in active set is 6, but you seldom come across an active set with 6 members. That's because, number one, in practice, when a mobile station moves around, it is very difficult for a mobile station to see 6 strong base stations. So that's topologically not very likely, okay? And number two, even if you have such a spot, it's so expensive to support 6-way soft handover because you need 6 copies of radio capacity and 6 times of the backhaul capacity. So that's why in practice, you just keep this number to be 2 to 3 at most. Most of the time is 2. Is that okay? Okay, so that's pretty much the soft handover, the base station controller side. Is that okay? So when base station controller receives this PSMM message, of course it wants to approve the request, but it has to check for available resource. The new base station, does that have the new channel on the radio interface? Does that have sufficient backhaul channel on the backhaul connecting to the new base station? So if everything is yes, if the resource-wise is permitted, then the base station controller will execute a handover by allocating one backhaul channel and allocating one radio channel. And the traffic frame will then go from both base stations to the mobile station. Is that okay? So that would be the soft handover. Okay. Now, perhaps let's take a 10-minute break, and then we come back to talk about the 3G. Okay, another way to support so-called packet switch data connection. So let's take a 10-minute break.
Testing. Okay, let's try to resume. So in the interest of time, I will skip the intermediate evolution story, although there are quite a lot of interesting stories, but let's not worry about this. And let's go straight to the UMTS, wideband CDMA. So let's see. Yeah, let's look at this picture. So for UMTS, this is a 3G system. So for 3G system, for some reason, they're going to rename everything. But technically, this they call the base station Node B. And they call the base station controller something called RNC, Radio Network Controller. And then mobile station is called UE, User Equipment. Okay? But they just changed the different names. And then again, this interface is the interface between the radio access network. To the left of this interface is called radio access network, consisting of radio network controller all the way to base station and mobile station. So this interface is taking care of all these radio-dependent functions, which I'm going to explain what we mean by this. On the right of this boundary is called radio-independent function. So it's connected to some kind of core network. Now, different from 2G, IS95 is a 2G network. For 2G network, the core network is just designed to interface to the public switch telephone network, which is the largest public voice network at that time, or even today. But for 3G, it's going to support both voice and data. For data, it's going to be packet switch data. So it has to, the core network of 3G needs to interface to two types of public network. One is the public voice network, public telephone network, same as 2G. The other is the internet, for example. Okay? But the challenge here is the PSTN is based on circuit switch architecture. The internet is based on packet switch architecture. So these are two different languages. So how would you interface the core network? How would you design a core network so that it can interface to these two very different networks? So that is actually a design challenge. Now later on you will find that, at least in the initial release, the core network is designed to be overlaid. So there are actually two layers of core network. One to interface to PSTN, which is circuit switch based. The other is to interface with the internet, which is packet switch based. So there are two layers of core network simultaneously. Now in later release, we call this release 5 or release 6. The core network, this two core network later is integrated into a common IP network. It's just one single all IP network that still interface to PSTN and internet. Then how do they overcome the challenge? Now, if this is an IP network, so IP connect to IP is easy. They speak the same language. But how does the IP network talk to or interface to PSTN? Remember, we say that PSTN has two interfaces. The data path expect dot wave format, PCM64. The signaling path, control path, expect something called signaling system number 7, SS7. But this is speaking IP. So how do we interface these two? The solution is to use some kind of gateway. So for instance, they use VoIP gateway, voice over IP gateway, to interface between an all IP core network and a PSTN network. Okay? Because of the proliferation of this kind of gateway, so that makes all IP core network possible. Okay? Now, like what I said, the core network in 3G is designed to be very versatile. On the public network side, it's designed to interface to different types of public network, like the voice network, like the internet. Okay? On the radio access interface, it's also designed to interface to different types of radio access network. For example, GSM, which is a 2G network, and UMTS, which is a 3G network. So therefore, the mobile phone, 3G mobile phone, usually by default they will support dual mode. So they can speak GSM, they can also speak UMTS. So therefore, that is the overall architecture for UMTS. So when they initially roll out 3G network, one of the challenge is the handover testing. When we say handover, we talk about soft handover, right? Soft handover is only between mobility between the base station in the UMTS radio access network, right? If we move from one UMTS base station to another UMTS base station, you have soft handover. This is called intra-system handover. But because it's dual mode, it also supports handover between radio access network. So you may be handing over from a 3G base station to a GSM base station as well. This is called inter-system handover. So the handover itself is also very complicated. Now this is how a base station looks like.
a 3G base station, macro base station. So you see that you have quite a lot of this filter, high power amplifier. These are analog, high power analog components built from discrete components. So they are not very well integrated. Okay, so they are bulky. They burn a lot of power. And then this baseband shelf are all digital circuits. They leverage on the Moore's law, VLSI. So therefore, you see that this baseband shelf, each shelf, if I remember correctly, each shelf can have 64 telephone channels. So it's highly integrated. Okay, so that's why I say that if you have a base station that requires a lot of this kind of radios, the base station will be very bulky and burns a lot of power. Okay, so this is, on the other hand, the RNC, radio network controller, in UMTS. So you see that there's pretty much no longer having any RF components because it's deep into the network. We are talking about radio network controller here. So it's pretty much consists of two items. One is pretty much a computer. So these are the computer modules. And the others are interfacing modules. Because you look at this base station controller, so it has to terminate a lot of protocols, as we say. Protocols are pieces of software running on a computer. So the basic processing involves computer. It also has to terminate a lot of backhaul from the node B, from base station. As I said, a base station controller usually can terminate hundreds of base stations. Okay? So each termination may be a T1, maybe a fiber, maybe an ATM. Okay? So you need to have quite a number of terminating circuit, interfacing circuit to interface with backhaul. And then based on that, you have lots of computer to host the protocol execution. Now also, because the base station controller is deep into the radio access network, if you have any problems with the base station controller or RNC, the outage will be huge because it will affect hundreds of base stations. So it will have huge impact. So in order to minimize the downtime for radio network controller, they usually have hot standby arrangement. So hot standby is like you have two pieces of identical computer, identical memory, running exactly the same pieces of software. So they have the same state, okay? So they're running simultaneously, feed with the same data, feed with the same parameters. So when anything happens on one side, the other side can pick up the processing immediately. So that's called hot standby. Okay, so with this kind of hot standby is a standard arrangement in this kind of very important network elements. But you don't have hot standby in the base station because that's too expensive. Okay, and also when the base station is down, it's only limited impact. Okay. So once again, this is a UMTS 3G architecture. In this chapter, we will still focus on the radio access network. Okay, and then we will talk about, in particular, we will focus on how the 3G network support packet switch data call processing. We talk about 2G call processing. When you press the send button and call somebody, you go through some handshaking, right? At the end, you set up a dedicated traffic channel for the conversation, and you pay for the airtime, right? If you set up a call for 2 minutes, you pay for 2 minutes of airtime, and that's the circuit switch. You own the circuit, and you pay for that. But for 3G, it's no longer circuit switch. It's something called packet switch. That means you can be logically online 24 hours, but you don't necessarily have to pay for so-called 24 hours of connection time. You pay by the packet volume you transmit. So that's how it works. But how is it possible to support such a packet switch connection in 3G? So this is the focus. Now, to go into before we go into further, let's spend some time to talk about radio network controller. So some terminology for the radio network controller. So radio network controller is actually a very important computer. Think of that as a computer hardware. Inside this radio network controller computer, it runs a very important protocol called radio resource control. So radio resource control, RRC, is a piece of protocol or a piece of software running on this hardware. Okay? Now this radio resource control will take care of a lot of, from its name, radio resource related functions, such as outer loop power control. So we talk about power control. Outer loop power control is part of the function of RRC. Okay? Soft handover, we also just talked about soft handover. Soft handover is also executed in the RRC. We talk about mobile detecting an event will send a PSLM message, right? So this PSLM message is actually generated from the RRC layer at the mobile station and terminate at the RRC layer at the base station controller. So this RRC layer at the base station controller for the soft handover function is taking care of the handover execution. So the handover execution we talk about is also a function of RRC. Okay, so we talk about out-of-loop power control, soft handover. So we won't talk about that anymore. So the new thing we haven't talked about is dynamic barrier reconfiguration. So this is the critical component to support packet switch connection for 3G. And that's why you can be online 24 hours without paying for airtime. Okay. Now, some terminology. Now, an RNC is called controlling RNC, and this controlling RNC is with respect to a certain base station. Okay. So every base station will have a corresponding controlling RNC. The controlling RNC will manage load and congestion control, admission control, code allocation, etc. Okay, so it's to control the resource associated with the base station, with the node B. Now, an RNC can also be a serving RNC, and this serving RNC is with respect to an active UE. So when a UE is in a connected state, it will have a corresponding serving RNC. Okay. So the serving RNC is to terminate the protocol stacks associated with the UE. Now I will explain what we mean by that. And RNC can also act as a drift RNC. But perhaps it's clearer to use this example. Now for this node B, this base station, this guy is the controlling RNC with respect to this base station. Okay, so that means this guy controls the radio resource associated with this node B. Now this guy is also the serving RNC because let's say the mobile set up a traffic channel at this spot. So the traffic channel, so this base station is the mobile's home cell. So the traffic channel will go through the base station and eventually through this backhaul connect to this serving RNC. So we say that to this mobile, when you start the call at this spot, the serving RNC for this mobile is this guy. So this guy acts as the controlling RNC for this base station, simultaneously serving RNC for this mobile. Is that okay? So as a serving RNC, all the related protocols from the mobile will terminate into this guy. Okay? Now, then what about drift RNC? Now the thing is, when mobile start a call is at this location, right? So it's natural to terminate the protocol at this serving RNC. But after you set up the call here, the mobile is moving, right? The mobile can move eventually to another base station, and this new base station is not connected to the same RNC anymore. Okay, so in this example, when mobile hand over to this new base station may be connected to another RNC, but the protocol anchor is still at this serving RNC. The serving RNC is still the same, okay, as before. So all the protocols should terminate at this spot. Okay, so then how do you do it? Because this guy is not directly connected to this serving RNC, so it has to make use of this RNC, act as a drift RNC. So the drift RNC is just a dummy. It doesn't terminate any protocols. It will just relay all the protocols through this interconnection to the serving RNC. So that means as the mobile drift away and away, the serving RNC will always be the same, okay, when you set up the call. So all the protocols will have to go through the drift RNC and deliver to a relay to this serving RNC to terminate and process the associated protocols. Okay, so that's the serving RNC concept. Is that okay? So that's those are terminology. So in short, the RNC, radio network controller, is a piece of computer hardware. And what matters is what are the software running on top of this hardware. And one important software or protocol stack, protocol layer is called RRC. So RRC is a control plane protocol, as I will talk about in a minute. And it takes care of the major radio resource related functions. Okay. Now I talk about protocol stack. Now in 2G, when we talk about circuit switch voice, the protocol stack is very simple. It's pretty much layer 1 connection. But when we talk about 3G, now it's a packet switch connection. So the protocol stack is more complicated than the 2G systems. Now first of all, this is the mobile side. The mobile side, you can think of that physical layer is usually implemented in the hardware, in the chipset. Okay? So it's a dedicated piece of hardware. In a mobile handset, there is also a computer, a microprocessor. The microprocessor will be responsible for the higher layer protocol. So usually layer 2, MAC layer onwards, these protocol stacks are implemented on a microcontroller. Okay? So again, we think of these as some software. So the software, just like your laptop, the software can be partitioned into two types of software. One type is what we call user plane protocol. These user plane protocols are the software that are involved in delivering your user payload. For example, you may have a laptop running a web browser. So the web browser, the application will be HTTP, TCP, IP. So these are the user payload. They will all come all the way from TCP, IP all the way to the user plane protocol like this and deliver to the other side. So all the protocol layers that are involved in every delivery of the user payload is called the user plane protocols. So user plane protocol consists of this MAC layer, layer 2, RLC layer, also layer 2. I will explain what they are trying to do. And then something called PDCP, and then user plane protocol like TCP IP. So these are examples of user plane protocol, okay, or data plane. Now that's one half. Now just like your laptop example, beside your laptop browser is the main user plane application. Beside this browser, you have a lot of the background applications running as well, right? Those are not visible, and those applications are not even involved in the daily delivery and in every single delivery of user payload. But they are background tasks that exist for various control functions. So this is also the same for mobile. So these protocols that are running in the background for various control functions is called control plane protocol. So the protocols can be partitioned into user plane protocol and control plane protocol. Okay. Now, you notice that no matter it's a user plane protocol or control plane protocol, the layer 2, which is MAC layer and RLC layer, remains to be the same. Okay. So let me explain briefly this layer 2 protocol. So those are common layer 2 protocols between the user plane and control plane. So now, perhaps let me explain this way. Now here, the terminology in 3GPP UMTS is like this. The interface between physical layer and MAC layer, they are called transport channels. So transport channel is a special name that refers to the MAC-PHY interface. Okay. The cook channel, the spreading channel that we talk about is the physical channels. Okay. But then between the PHY and the MAC, this is called transport channel. You can think of them as some virtual channels. Okay. Between the MAC and PHY, so you can have more than one transport channels, as we'll talk about later. Now between the MAC and the RLC layer, they are called logical channels. Okay, so these logical channels refers to the MAC-PHY, the RLC and MAC layer, and also above the RLC layer. They are also called, so if this is an RLC layer, radio link control layer. Below this is called logical channel. Above this is also called logical channel. Now the difference is, this logical channel below this is supported by, through the MAC configuration, mapped to one of these transport channel. And then through the physical layer, mapped to some cook channels or physical channels and deliver through the over the radio interface. Okay. So because this radio interface, when you deliver a packet over the wireless interface, you will have error probability, right? As we just talked about, the typical error probability will be 1% or 0.1%. Okay. So that means once a while you have packet loss due to transmission errors. Okay. So that means this logical channel is not reliable. This is unreliable. You may have packet loss due to transmission errors because this is through the radio interface. Now, however, most of the application on top of these logical channels require reliable channels, reliable connections. So how do you turn an unreliable logical channel into reliable logical channels? Understand my question? Given that this is unreliable, what can you do to make it reliable here? If you study computer networks, the standard approach is what? You can do something called ARQ, retransmission. So you keep a retransmission buffer. So every RLC packet coming in here, you put into the buffer, transmit it out, but you keep this transmitted packet in the buffer until you receive an ACK from the other side. Okay? Once you receive an ACK, you can remove this packet from the buffer and transmit a new packet. Okay? If after some time out you don't receive an ACK, you assume the transmission is lost.
then you retransmit. You retransmit until you receive an egg. So that's the standard retransmission mechanism, right? In computer network, you also have something like this. So through this retransmission mechanism, although this is unreliable, this becomes reliable. Is that okay? But there's no free lunch. If this is very unreliable, then although this becomes reliable through retransmission, but the penalty of this unreliable logical channel becomes latency. Because on average, you may have to retransmit 5 times to get through one packet. So the penalty becomes the latency. Okay? So this is the role of RLC. So in the RLC, they have a retransmission buffer, trying to convert an unreliable logical channel into reliable logical channels. Okay? Now, transport channel is any logical channel can be mapped to different types of transport channels, which I will explain later. And the mapping is through configuring the map layer. So this is one good or bad things about 3GPP protocol stacks. These protocol stacks are designed in 3G, but they maintain the same architecture in 4G and 5G. Okay? So that means if you look at the spec in 3G, 4G, and 5G, you see the same terms as transport channel, logical channel, map layer, RLC layer. So they basically inherit across generations. Now, the design philosophy is they provide, from this figure, you have different types of transport channels, different types of transport channel in uplink and downlink, and then different types of logical channels. And this map layer will allow very flexible configuration to map the different logical channels into different types of transport channels. Okay, so these are possible mappings. So this flexibility comes at a price. If you are the one who have to write or implement the protocol stack, you have a very complicated protocol stack to write because you have lots of options and lots of boundary conditions to check. If you look at the standard, just describing the map layer to physical layer mapping, the standard is very thick, few hundred pages. And that's because you have to provide a lot of mapping options and lots of configuration. Okay? So to the one that developed the protocol stack is super complicated. But to the one that are just user of this protocol stack, you will find it very flexible. Okay? You have lots of options to configure how a logical channel can be mapped to transport channels. Okay? Now, I will talk about this later. So back to this protocol stack. So RLC and map layer. So map layer is to provide flexible mapping between logical channels and transport channel here. Okay? And RLC layer is to map an unreliable logical channel into reliable logical channel. Okay? So both the user plane and control plane use the same layer 2 protocols. So the difference between user plane and control plane are who are the applications running on top of these reliable logical channels. Who are the guy using these reliable logical channels? If this is a user plane protocol, so this guy will be user plane protocol using this channel, sitting on top of these logical channels. If this is a control plane protocol, then this guy will be coming from a control layer protocol, sitting on top of these logical channels. Is that okay? So that's basically the idea. So this is just a vertical slide across the UE side. Okay, so you see, if you look at the control plane, this boundary, this horizontal boundary is the boundary between, below this boundary is radio dependent resource control. So RLC is below this boundary. As I said, right, RLC is a piece of control plane protocol running on the hardware, RNC, serving RNC. So this guy takes care of outer loop power control, takes care of soft handover, also takes care of something called dynamic barrier reconfiguration. Okay? Now, above this layer, this is not the end. Above this guy, there are also other control plane protocols. These control plane protocols are responsible for core network radio independent resource. So this is for circuit switch domain. This is for packet switch domain. So we'll talk about this in the next chapter. So for instance, MM stands for mobility management. So we talk about briefly location update request, right? So through this location update, the infrastructure will know where you are. So the location update mechanism is triggered or managed by this mobility management. Okay? This is for circuit switching, and this is for packet switching. Remember in the initial release, I say that the core network, they take an overlay approach. So that means they have one core network, which is circuit switch based, and one additional parallel core network, which is packet switch based. Okay? So these are the protocol stacks corresponding to the circuit switch based core.
And these are the protocol stack corresponding to the packet switch core. Okay? Now you may notice that there is something called SMS. So if you send short messages, these days you seldom send short messages. But in those days, the short message is very important revenue for 2G operators. Just like today, you used to send text messages. In those days, you don't have WhatsApps. But in those days, people send short messages. And they usually charge $1 per short messages. So that's why they earn a lot of money from short messages. And short messages is somehow, by design, not a user plane protocol. It's actually a control plane protocol. Okay. Anyway, so we'll worry about this part later in the next chapter. But here, let's focus on the radio resource related protocols. Now, this is, before I move on, so another remark is, I think I hope you guys have heard about OSI 7 layers, right? In your bachelor, undergraduate. In computer network, you usually study the computer network protocols by dividing into layers, right? So you have layer 1 physical layer, layer 2 link layer, layer 3 network layer, blah, 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 right? So that's called OSI 7 layers. But I found that most of the students, when they try to understand the OSI 7 layers, they only have half of the picture. That is what I call the vertical picture. So for example, if this is the protocol layers of a mobile station, you expect layer 1 will do something, layer 2 will do something different. You expect across this vertical slicing, each layer of the protocols will do something different, right? So that's partially correct. But if you only have this vertical picture, you may not be able to fully understand the design of the protocol stack. For example, later on you will see that, now as I said, our LC layer, this guy, will have retransmission, right? So if you send our LC packet through the radio interface and it gets corrupted, this guy will take care of retransmission, right? So there is retransmission function in the RLC layer. Now in the user plane, you may have TCP IP. Now if you study TCP before, in TCP layer, you also have retransmission function, right? If you lose a TCP packet, the TCP layer will take care of retransmission, right? So now if you only have vertical picture in mind, you come into a question that how come you have two layers doing the same thing, retransmission? You have this layer doing retransmission when you have packet loss. At the TCP layer, you also have retransmission function at the TCP layer. Understand what I mean? So is it a duplication of function? Right? Of course, it's not a duplication of function. But if you only have a vertical picture in mind, you will never be able to understand why you have two layers doing the same thing, retransmission. The missing layer that I come across from interaction of students is horizontal layer is also important. Horizontal peering. Okay? So in addition to asking what are the functions of this layer and that layer, you expect each layer to play different roles, to play different functions. In addition to this, you should also ask or worry about or be mindful about who are the terminating peer for a particular protocol layer. For example, this RLC layer terminate at where? RLC layer terminate at where? Each layer may not have the same terminating end. Okay? So you also need to have a horizontal peering concept before you can have a complete understanding. I will explain this later. Now, if you just look at the user plane, so on an end-to-end basis, so this is a dissection. So layer 1 is the physical layer, the spreading, despreading we talk about, usually implemented in a chipset. So the map layer and RLC layer is the common layer 2, right? So once again, RLC layer is to turn an unreliable logical channel into reliable logical channel by retransmission. Now, this is a user plane. So on top of this RLC, so who are the ones using this reliable logical channel? For the user plane protocol, it's the PDCP. PDCP is actually an IP header compression. So you know IP, if you study IP protocol, the IP header is very, very large, right? A few tens of bytes. So because the radio interface is very limited in terms of the capacity, so you try to, so this layer is trying to compress the IP header. So you don't send the entire IP header over the radio interface, okay? So this PDCP terminates at the serving RNC, okay? So this guy compresses the IP header so that you don't send the entire IP header to the radio interface. At the RNC, at the serving RNC, this guy regenerates the IP header, okay? So that the complete IP packet will get delivered to the core network and to the internet, okay? So that is basically the function of PDCP. On top of PDCP, then will be IP, and then TCP, and maybe HTTP. So this is the example of user plane protocol. So as I said, these protocol layers are involved in delivering of user payload, every single user payload. Okay, so that's why they are user plane protocol. On the front end, put it this way. And then different layer will have different terminating parties, right? As I said, for example, PDCP will terminate into the serving RNC, okay? But then IP will be transparent to the serving RNC. IP will terminate into the IP core, okay? This is a gateway router, gateway GPRS support, no, GGSN. So that is the gateway router at the packet switch version of the core network, okay? So IP will terminate here, and then TCP will terminate to the server directly, bypassing all the routers in between. So different layers will have different terminating end. So be mindful about this as well, okay? So this is a user plane. This is a control plane on the other hand. For the control plane, you see the common layer 2, RLC. The difference is the guy sitting on top of this reliable logical layer will be RRC, radio resource control. So radio resource control will take care of soft handover, out-to-the power control, and in particular, in this context, dynamic barrier reconfiguration. That will be the critical component to support packet switch connection for 3G. Okay? And on top of this line, you have GMM, GPRS mobility management, and then session management, etc. Okay? So these are the core networks. So you see that this control protocol on top of RRC will terminate directly into the core network. Okay? Whereas the RRC will terminate into the serving RNC. So using the example of soft handover we just explained, the RRC layer of the mobile will generate a PSMM message when you come across an add event. Okay? When you come across an add event, the RRC layer of the mobile will generate a PSMM message, pilot strength measurement message, and this PSMM message will deliver to the serving RNC RRC layer. So the PSMM message, handoff direction message, handoff completion message, they are RRC specific signaling message exchanged between these two peers. Okay? All right, so this is control plane protocol. So as I said, in order to understand 3G, we also need to understand these several things. Packet switch call processing, the notion of transport channel and logical channel, closed-loop power control, and handover. So these two things we have talked about in IS-95, so we won't spend time on this. So we just focus on the first part, packet switch call processing. Okay? So as I said, the terminology is standardized in 3GPP. So for wideband CDMA, for LTE, for 5G, and future 6G, the architecture is pretty much the same. So transport channel always refers to the virtual channel between PHY and MAC. Okay? So there are different types of transport channels. Logical channels, on the other hand, refers to another level of virtual channel. Okay? And then RLC layer will convert an unreliable logical channel into reliable logical channel through retransmission. So every RLC, every logical channel has an RLC object or instantiation. Okay? So these are different names. Don't worry about these terminologies. So, and also different transport channels. So this is just to say different types of transport channels will be multiplexed into one or more physical channels. Okay, so there are different ways to do multiplexing, and these are specified in the standard. So never mind the details. Don't worry about this. So now let's focus on packet switch call processing in UMTS. Now in 2G, the major applications are voice. For voice application, so let's look at the motivation, why we want packet switch connection. If you look at 2G, to support voice communication, this is a bit rate, this is time. So most of the speech encoder or voice encoder, they have CBR. So most of the voice encoder, they are CBR, constant bit rate encoder. So the output bit rate, the source bit rate produced by the compressor speech encoder is pretty constant. So this is a demand. Now if you have a constant demand, then in 2G, the best way is you set up a channel, the traffic channel, which is constant bit rate. So this is a traffic channel. Okay, you set it up, the demand will always be satisfied. Okay, so therefore, the best way to accommodate this kind of steady demand is circuit switching. You set up the traffic channel, delivering a constant bit rate, and you own the channel. If you own the channel for 2 minutes, you pay for 2 minutes, and that's it. Okay. So for voice, this is fine and very, very important and very, very logical. But for data, let's say you do video streaming, so different types of data, but let's say for video streaming. As you know, most of the video encoder, they are VBR, variable bitrate encoder. That means the source rate generated by the video encoder changes from time to time. So the demand may be like this. Okay, the demand may be like this if you do a video streaming. So now, if you only have circuit switching, if you try to use 2G connection to support this kind of bursty traffic, then you have problems. So for example, if you have circuit switch network to support this kind of video streaming, you can set up the traffic channel with this rate. Now if you set up with this rate, what's the problem? Now during the peak, you can meet the demand, right? That's fine. Okay? But during this time, you have underutilization, right? You have minibus that have 100 passenger seats, but during this time, you only have a few passengers, right? So most of the bus is empty. You have to pay for the bus. So you have underutilization. So this is expensive, right? If you do it this way, this is an expensive way to support video streaming, right? Okay, so if you do not do it this way, what about you still do circuit switching, but now you set up a traffic channel with the rate meeting the average demand. So this would be the rate equal to the average demand. Now if you do it this way, what's the problem? Now, it may or may not be a problem, depends on the type of applications. Now, if this application is not delay sensitive, if this application is delay tolerant, okay, then during this time, these are the excess passengers that cannot get on the bus, right? Okay, so this circuit switching is just like regularly, every 20 milliseconds, I have a bus with 50 passenger seats, okay? So during this time, the number of passengers is more than 50. So these are the overflow passengers. So what can you do? Now, if they can wait, then they can wait to get on the next bus. The next bus has less demand, right? So you can put this peak in those other locations. So on average, you can still deliver the throughput, right? On average, the number of passengers will meet the will be equal to the number of passenger seats on the minibus, right? Over a long time. Okay. However, this means this excess passenger or overflow packets, they need to be buffered and deliver at some other opportunities, right? But buffer cause delay, right? So if this application does not mind delay, let's say it's the file transfer, then that's fine, that's probably okay. But if this is a video streaming is real time. That means if you deliver the video packet 10 seconds later, that packet will be useless, right? Every packet has a deadline. Right? So that's the nature of video streaming. So for that, you are not allowed to wait, okay? You don't have the luxury, because if you wait for empty buses to come, by the time you deliver these passengers, they will be outdated already. The deadline expires, so those passengers will have to be dropped anyway, okay? So for video streaming, this is not an option. If this is not an option, what can you do with this? If they cannot wait, then you still deliver a circuit switching connection with this kind of average bit rate. Then during this time, what can you do with this excess passenger? You can only drop it, right? No other ways. So this guy has to be dropped, okay? Then in this case, the video streaming quality will be not very good, right? Because whenever there's a peak coming in, there will be massive packet drops, and you will suffer a lot in the video streaming quality. Okay, so that's why there's a problem associated with circuit switching. Now, on the other hand, with packet switching, what do we want to do? With packet switching, we hope that the radio resource allocated to support this connection can be dynamic. Okay, it's on demand. So when there's low demand, we provide a circuit, a connection that has a very low bit rate. When the demand comes, we increase the data rate of the, so the ideal case is to follow the envelope like this.
So in this way, we can always have 100% utilization, and we can deliver all the passengers as it comes, right? But the challenge is, what is the challenge? So this is the ideal situation, cannot be realized. The challenge is, think about the video streaming. Are you able, let's say you are now standing at this time. Are you able to predict when the next burst will come? No, why not? You think about the video, right? So why suddenly you have a huge burst of data? So video encoding, you know, the way they encode the picture frame is not on a frame-by-frame encoding, right? So what they encode is the difference between the two frames, right? So you take this frame with a pixel, you take this other frame, you subtract each of these two neighbor frames together, and you only encode the difference. So the amount of data generated depends on whether the difference between two frames is a lot or not, okay? And that depends. If you're watching a movie, if the movie is very boring, like what I'm doing here, I'm just standing still, not moving, just talking. So the difference between this frame and the next frame is very small, right? So in this case, the video encoder output will generate very small bursts of data. But if I start running around, right, then suddenly the difference between this frame and the next frame will be a lot, right? And then you will generate a huge burst of data, right? So supposedly, if you're able to predict when the next burst is going to arrive, this is the same as you are able to predict how the movie would go, right? So that is usually not possible. So you cannot predict when the next demand will come. But at the same time, when you set up the radio resource, when you change the radio resource in the connection, you always have latency. You always have delay, right? So the delay can never meet the demand. So by the time the demand comes, your bandwidth will be lagging behind, okay? So, so that's why this is an ideal configuration. So different systems have different ways to provide this kind of packet switch connection. The goal is like this, but it's never perfect. Okay. So now we're going to see how 3GPP, how the 3G system, in particular the dynamic barrier reconfiguration, accommodate this packet switching demand. So you want to change the radio resource associated with the demand. Okay, so you want to provide sufficient radio resource when demand comes, and you want to release the radio resource when there is no demand. Okay, you don't want to have a fixed commitment of the resource. You want to have a dynamic arrangement of the resource. Now in 3G, when you set up a call, you have 4 quality of service classes. The first one is called conversational class. This is for real-time voice communication. For example, you may set up VoIP. So for VoIP, the requirement is very stringent. So the delay for VoIP is less than 15 milliseconds. Okay, so it must be real time. The next one is streaming. So for example, real time video streaming. That is the next quality of service classes. The delay is about 200 milliseconds. Okay. The third class is interactive class. That is, for example, when you browse a web, when you click the link, you expect very responsive interaction. Okay. The fourth one is background class. Background class is basically no delay requirement, okay? Best delivery, non-real-time traffic. So when you set up a packet switch connection, you can actually declare these 4 different classes. And the base station and the infrastructure will allocate the resource according to your priority of the classes, okay? Now, so now let's look at how packet switch call processing is done. So in a UMTS, again, let me define a few terminology. The first one is called radio barrier. So I need to define what is radio barrier. So we talk about logical channel, right? So when a UE is connected to the serving RNC, the virtual connection between these two parties is called radio barrier. It's a logical connection, okay? Just like in fixed line network, when you create a socket using TCP, we can say you have an activated socket. So that activated socket means you have a logical connection between the two TCP layers, okay? But having a logical connection, meaning that you are online, doesn't mean you always have physical resource associated with that. So the question is, you can be online. So that means you have an activated radio barrier. That means you're online, logically. But the thing is,
below this logical layer or the radio barrier, what kind of transport channel you're going to support this. And so this has to be supported by some kind of transport channels. There are two major types of transport channel. One is called common transport channel. The other is called dedicated transport channels. So from its name, common transport channel means those are the common channels shared by all users in the network. Okay? So you don't need to set it up. Just like in IS95, we talk about paging channel, that sort of stuff, or access channel in the uplink. So those are set up initially, and those are shared by all users. So you don't need to set it up. Okay? Dedicated transport channel, just like dedicated traffic channel, require setup. Okay? So it requires some kind of, just like what we talk about in the call processing in IS95. You require some handshaking and set up, exchange the protocol to set up the traffic channel. Same here. In a transport channel, if the dedicated transport channel requires setup, and you need to pay for this. Okay? So there are two types of transport channel. Now some names for you. In the downlink, this is called fetch, fast access channel. This is the downlink direction. This is a common channel similar to paging channel. Okay? So this is shared by all users in the downlink direction. In the uplink, it's called random access channel, RAC. So this is the same as the access channel in the uplink that we talked about before. Okay? So these channels are set up for you when you bring up the base station. So you don't need to set up further. Okay? So no setup. So that means they are free to use. Okay? So these are the dedicated transport channel, DCH. So for uplink and downlink. Okay, so these are the table to show you the breakdown of the transport channel. So DCH stands for dedicated transport channel. So dedicated transport channel applies to both uplink and downlink. Okay, so with dedicated transport channel, just like traffic channel, you can have fast power control, fast closed-loop power control. You can have soft handover. Okay, you can have soft handover protection. But then you have a high setup time. You need to go through handshaking to set it up, just like traffic channel. So that's why this is good for high traffic demand, because with high traffic volume, it's worthwhile to spend the overhead to set it up and then deliver a huge chunk of data, right? On the other hand, for common channel, common transport channel, in the uplink it's called random access channel. So it's in uplink. There is no power control for random access channel, no soft handover for random access channel. So good thing is there is no setup time. Whenever you want to use it, just transmit on that. So this is good for small bursty amount of data, okay? Because you don't need explicit setup, okay? On the downlink, common transport channel is called fast access channel. This is the downlink counterpart of the uplink random access channel. Okay, again, open the power control. No soft handover, no setup time, so that's why it's good for small bursts of data. Now, these other types forget about this other type, this is irrelevant for now, okay? So these are the two types of transport channel, just for your information. Now, the idea is the so-called dynamic barrier reconfiguration, or the so-called packet switch connection for 3G is the RRC, radio resource control. Think of that as a manager. The manager has to monitor the traffic demand all the time and assign appropriate types of transport channel to support this active radio barrier. So this radio barrier can be active for 24 hours, but the underlying transport channel to support this radio barrier change from time to time between common and dedicated transport channel. Okay, so who enforce the change is this RRC. Okay, this RRC is the guy who try to drive the change. So the RRC, think of that as a state machine. It has two major states. Idle, when the RRC is in idle state, that means there is no active connection, not even the radio barrier. The mobile is offline. When the mobile is offline, RRC is in idle state. Now when the mobile is online, that means you have an activated radio barrier. The RRC is in RRC connected state. So this connected state means the mobile is online. Okay? But there are different substates in the connected state. we just need to worry about this two, cell DCH and cell fetch. Now, if the RLC connected state is in this cell fetch substate, that means this activated radio barrier is supported by a common transport channel. Okay. On the other hand, if this activated radio barrier is supported by dedicated transport channel, then it will be in cell DCH state. So during a 24-hour session, depending on the traffic demand, this RLC state in the connected state will change from cell DCH on and off to cell fetch state, triggered by the traffic volume changes. Okay. So now let me give you an example. Now suppose you have a huge, so this is a connected state. The radio barrier is connected from the beginning to the end. Okay. But now here this is showing the different traffic volume. So let's say initially you only have a small burst of data to send. Okay. Over this radio barrier, only small burst of data. Then your radio barrier is now supported by common transport channel. Okay. So therefore, and the RLC state is in the cell DCH state, cell fetch state. All right. So far so good. You only have small bursts of data, so small influx of customers. Suddenly, you have a huge demand. Okay, so suddenly this, let's say, this is the RLC layer supporting this logical channel. Okay, so suddenly you have a huge amount of data to send. Okay, so how do you know? There is an RLC here. RLC is running on the control plane here. So RLC is the manager to enforce the change. But the change has to be triggered by traffic volume changes, right? So how would this guy know there is a change in traffic volume? How do you know there's an influx of traffic? Well, one obvious place is you remember in RLC, there's a retransmission buffer, right? So initially, when you're in cell fetch state, this is very low. This output rate of the server is very low. The input rate is low. So the buffer is balanced, right? So there's no problem. But suddenly, if you have a huge influx of demand, and you still keep the cell fetch state, low output, then what will happen? The queue will queue up, right? The queue level will grow. This is like in a supermarket. Let me use a supermarket analogy. So let's say in the cell fetch state, that means in the checkout counter, there is only one active checkout counter. Okay? RLC is the supermarket manager. So far so good. Okay? There's not many customers in the supermarket. So one checkout guy would be able to entertain the demand. But suddenly there's a huge flush of customers entering into the supermarket. Okay? This RLC manager, supermarket manager, look at the checkout queue, right? So now the checkout queue is very long. Then what happened? That means there is a huge demand. The single checkout counter is not sufficient. Then this supermarket manager will activate the change. Instead of supporting the connection using common transport channel, it will switch to dedicated transport channel. That means it will open up more checkout counter. Okay? So that means in response to this huge in traffic demand, the RLC will configure a dedicated transport channel to support this connection. So therefore, the output rate becomes high. That is triggered by this. Okay? So the RLC monitoring the RLC buffer. This is like the supermarket checkout counter. Realize this is a long queue. Okay? With a long queue, that means there's a huge increase in demand. Then RLC, the supermarket manager, will take action to configure a dedicated transport channel to support the logical channel, to support the radio barrier. So therefore, it will take some time to set it up, but after you set it up, then you can have a huge influx of delivery to meet this, to entertain the demand, right? So the demand is satisfied, but suddenly, okay, in the supermarket analogy, the influx of customer is now finish their shopping and leave the supermarket. Then in that case, you still have 10 checkout counter open for that. Then in that case, what happened? You are the supermarket manager. Well, you notice there's a decrease in traffic demand, right? How do you know there's a decrease in traffic demand? You look at the checkout queue, most of the queue are empty, right? So the queue is empty in this case. So if the queue is empty, you start a timer. If the empty is still maintained after a timer expiry, then you take action, saying that, okay, the demand is gone. Then if you're the supermarket manager, you will redeploy those checkout counter
to do something else, right? Same here. Then you will release the dedicated transport channel and replace with common transport channel to support this connection. So that's why the RLC state changed from self-fetch state initially, and in response to increase in traffic demand, change to cell DCH state. Maintain in cell DCH state for a while until the demand is gone. Okay? Then the buffer empty for an extended period of time. Then the RLC manager will then change it back to self-fetch state. And now the logical connection is now supported by common transport channel again. And then you can deliver small bursts of data. So this is how the underlying radio resource switch back and forth in response to the change in demand. But in this switching, the application on top, the user plane application will be transparent. Okay? The user plane application will be transparent to this switching. The user plane will just see an active connection all the way. Is that okay? Just like the application in a TCP socket, we always just see a connected socket connection all the time, even if your connection is changing back and forth. Okay? Now, so to set up a packet switch data connection, so let me finish this part and then we'll stop. So like what we talked about in 2G, when we press the send button, you have some kind of protocol going on before you can set up a socket switch connection. In 3G, it's the same process. How do you get online, get connected? There are 2 steps involved. First step is you have to set up or activate an RLC connection. What do we mean by this? Now, so this first step must be triggered by UE. In particular, is the RLC layer at the UE. The RLC layer, similar to when you press the send button. In this case, when you trigger a connection request, the RLC layer at the UE will send an RLC connection request. And this connection request will go through the random access attempt, just like in 2G, you have to go through the access port. And through one of these retransmission, you will get this message to the base station and then eventually to the base station controller and to the RLC of the base station controller. So then in this case, so let's show in this picture. After step 1, then this, what we call signaling barrier is connected. Signaling barrier means the logical connection in the control plane. Okay? And the guy sitting on top of this signaling barrier will be RLC. So that's why after step 1, the RLC is connected. That means the RLC layer in the UE and the RLC layer in the serving RNC can talk to each other. Okay? The signaling plane is connected. Now, but this is only the control plane. Okay? The user plane is not yet connected. So the second step is to set up the radio barrier or the data barrier for the user plane. So now for step 2, on the contrary to step 1 is UE trigger. But step 2 is serving RNC trigger. So in step 2, the RLC layer in the serving RNC will send a radio barrier setup message, okay, to the RLC layer in the UE. Now the 2 RLC layer is connected, right? So these 2 layers can exchange a signaling message. So by sending an RB radio barrier setup message from serving RNC to UE, then the protocol configuration now becomes this. You have an activated signaling barrier. On top of that, you have RLC running. So that's the control plane. And on the data plane, you have an RB1, data barrier activated as well. Okay? Now in this example, these 2 radio barrier or 2 logical channels are multiplexed into a common transport channel. Okay? So this is one possibility. So therefore, after you set up step 1 and step 2, you are online. The data plane is online, connected. But then your RLC state is in a self-fetch state because the common because these 2 active radio barrier are connected through, supported through a common transport channel. So previously, I say that the map layer has provided very flexible mapping. This is what I mean. You can have 2 radio barrier mapped to 1 common transport channel. You can have, later on we have more examples, multiple radio barrier mapped to different transport channels. So this is through the flexible configuration of the map layer mapping. Okay? Any questions? So this is the protocol. So in step 2, the RLC at the serving RNC has to send this radio barrier setup to the RLC at the UE. Okay? And after that, the UE will respond with an RB setup complete. So this 2-way handshaking will synchronize the configuration of the map layer. Okay? So that both the UE
and the serving RNC have the same configuration and same mapping of the MAC layer. Is that okay? So after step 1 and step 2, we say that you are online, connected. Okay? So I have to stop now, but next week I will talk about the remaining stuff like the dynamic barrier reconfiguration. How do you change? What is the mechanism to enforce the change of this configuration in response to traffic changes? Okay? And then after that, we'll talk about the core network services. Okay, so let me stop at this point.